Hello everyone, welcome to this channel. This question is from Olympiad Pathfinder, Chapter 12, Build Your Understanding, question number 13. A thin dielectric rod of mass m and length L carrying a uniform positive charge Q, moving with a velocity u, enters a two-section region of electric field. Both the sections are of equal thickness d, where L is greater than 2D, each and have electric fields of the same magnitude E that points opposite to the initial velocity of the rod in the first section and in the direction of the initial velocity of rod in the second section. So assume charge distribution of the rod remains unaffected by electric fields and ignore electromagnetic induction due to motion of the charged rod. So part A, what should be minimum velocity u of the rod be so that it will completely pass through both the sections? Part B is if the rod enters the first section with a velocity which is double of that obtained in the previous part, means part A, what speed will it emerge out of the second section? Let us solve this question. This is the rod. The length of the rod is L, mass is m, and it is projected with a velocity u parallel to the E field. E field starts from here, from this boundary, and ends at here. If you notice, E field as per question is given that in the first section it is opposite to the motion of the direction of motion of the rod. So in this direction. In the second section it is towards the direction of velocity of the rod. And the D field width is D for each of the field. Like for first section it is D, for the second section also it is D. Since it is carrying a charge Q on it, we can get the linear charge density lambda, that is equal to Q by L. Now let us consider the case when the rod has entered by a length R inside the first section of the field. Remaining part is out of the field. So on this R section, the total charge will be lambda into R. And because of this charge on the rod, the force due to E field will be working in this direction, opposite to the direction of motion of the rod. That has been shown here as FER1. So what will be this force? This force will be the charge on R section of the rod, that is lambda into R, into the magnitude of the E field, and the force is in this direction. Now the rod further moves by a distance dr. It's very small, infinitesimally small, in the first section of the field from R. So in moving from R distance to R plus dr, the work done by the E field will be in the negative direction of the direction of motion of the rod. So it means the rod will lose its energy. So how much energy will be lost for dr movement can be given as FER1 into dr. FER1 we know that the charge lambda r into E to dr. So we can calculate the energy loss when the rod just enters in the first section of the field and travels to a distance till d length. That can be calculated by integrating the r for 0 to d, and we will be getting this equation number 3. Value is lambda e small d square divided by 2. So this much energy is lost in entering the rod from 0 to this distance. Now, after the d distance of the rod has entered, because of motion, it will further go and start entering into the second section. The moment it enters into the second section, in the second section, the part of the rod which will be inside the second section will be having the charge on it, and the force will be in the direction of the E field. So FEX2. So this diagram has been shown when the rod has entered by a distance x inside the second section of field, and D section is already inside the first section of the field. So when the rod is in this condition, what will be the net force on the rod towards the right direction, towards the direction of the motion of rod, will be FEX2 minus FED1. FEX2 we know that lambda x will be the charge on this portion into E field. FED1 we know that lambda d will now be the charge on this rod into E and will be acting in this direction. So we can comfortably write net force acting on the rod in this condition as this, equation number 5. So you can see that till the time the rod had just entered till d distance in the first section of the rod, only the retarding force was acting, and it was increasing from 0 to d distance. But moment a part of the rod enters into the second section of the field, a force in the rightward direction, along the direction of motion, will come up, will start acting on the rod, and it will start reducing the retarding force that is being exerted in the first section of the field. So again, if we consider that now the rod has moved by an infinitesimally small distance dx towards the right in the second section, so what will be the work done in this case? So work done will be net force into dx. That is equation 6. Now if we integrate this equation for the value of x from 0 to d, we will be getting the total work done W1 for the rod movement from this boundary, that is from x is equal to 0 to d, and that will be minus lambda ED square by 2. So what will be the total energy loss for the situation when the rod has entered d distance in second field and d distance already there in the first section of the field? The total energy loss for the situation will be WTL if we write. The total energy gained by the rod in entering into the second section of the electric field by distance d plus total energy lost by the rod in entering first section of the electric field by a distance d. So we can write it as minus W1 plus W. Why this negative sign has come? Because we are considering the loss. Here W1 has been represented as gained. So gain is opposite to the loss. So W1 has come with the negative sign. So this will be the total energy lost. And this we are writing, we have given the name as equation 8. Now when the rod is having d length inside the first section and d length inside the second section, so the force on the rod on the right side, means along the motion of it, will be equal to the force acting opposite to the direction of motion of the field, because the charge will be lambda into d in first section and lambda d in second section. E field is in this direction, so lambda d into E will be acting in this direction, and for this section it will be acting lambda d into E in this direction. That is why it is written over here shown as FED1 is equal to FED2. So it means when till the time the rod is entirely into the electric, both the section of the electric field together, there will not be any force acting on the rod, and the rod will keep continuing moving with the same velocity as it has reached here. So now we have got that for this situation to reach, energy lost in the rod is this much, and initial energy before entering into the E field was only the kinetic energy, that was half mu square. So the rod to pass out of both the section of the E field, it is important that the kinetic energy of the rod outside the electric field should be greater than or equal to the total loss of energy inside the field, this equation. So from here we will be getting U is greater than or equal to 2 small q E d square in numerator divided by L m whole thing in bracket square root. So from this expression we can say that U minimum should be d into this. So this will be answer for your part A. In part B, the question is referring to the entire rod to come out of second section of the electric field from the equation 3 and 7. It will be W plus W1 will be 0. Means there is no residual work done left to add up with the kinetic energy of the rod. It means the velocity with which the rod was projected, it will come out completely from the second section with the same velocity, because kinetic energy is same, no work done, no additional work done, so no addition of energy. So if, as per question, the rod was projected with 2u velocity, so it will come out also with the 2u velocity, and we can put the u minimum. So this will be your part B answer. Please go through the write-up to understand easily. In case any doubt, please do write in the comment box. Thank you.